for joining us today for our talk on virtual machines on Kubernetes pods, one more layer of security, right? And also, we want to thank you for welcoming us in Tel Aviv and at BlueHat IL. We are delighted to be here. So we're going to start by introducing ourselves. My name is Diane. I'm a security engineer at Google. I work as a vulnerability researcher on cloud products. So in other words, our motto is Hack Cloud. And I focus on low-level platforms such as the hypervisors, the firmware, operating systems. Last year I presented here on Hyper-V fuzzing. This year it will be a bit of a different topic. And I'm also an active community contributor, enjoying participating at, for example, reviewing papers for conferences, being a proud member of Women in Security Associations also.
And my name is Julien, and I'm also a security engineer at Google. I focus on cloud product hardening, so we also try to find vulnerabilities in product, but we also look at root causes of vulnerabilities and to propose mitigation and hardening solutions to tackle vulnerability classes at scale. And I'm also a member of the blackalps.ch organizer, and our CFP will open soon.
So what are we going to talk about today? First, let's go back to the title, Virtual Machines on Kubernetes Pods. First, what is Kubernetes? So I don't know, in case some people have never heard of it, have never used it, you can think of Kubernetes as being kind of Docker on cloud platforms. So in other words, it's an open source system for automating the deployment and scaling and management also of containerized applications. And KubeVirt is an add-on to Kubernetes that enables running virtual machines on Kubernetes pods. So I'm going to insist a bit on that. We are not speaking about Kubernetes running possibly on virtual machines. We are speaking about virtual machines running inside Kubernetes pods. And also, you may wonder why. Why do that? This is to support some customers who used to run their applications on virtual machines and wanted to port those use cases to Kubernetes and to make it more seamless for them to port. So some people may think, I'm not saying this is true, but some people may think that containerization implies sandboxing, and some people may think that virtualization means more security. OK, so those people may think, oh, great, so then there's more security. So this is kind of sandboxing plus, awesome. And actually, we wanted to question that, and that was one of our main motivations to look at that stack. So could it be deceptively secure? And also, we are working at Google, and this is used on Google Cloud, so we wanted to make sure that the product was safe, secure. It's used, for example, for NTOS, for distributed cloud edge, and hosted. And also, we have the support of an internal engineering team, which helped quite a lot. And as it's kind of new, we are not going back in time too far, but that was also a motivation, like looking at some new piece of code that does virtualization. So first, we're going to cover some background information on KubeVirt today. Then we're going to talk about our findings, what we broke, then talk about the remediation and hardening, how to fix it. So first, some background information on KubeVirt. Let's make sure to start with that we speak the same language. So first, you may have heard me talk about pods. Pod, container, pod, the same. Also, we're going to talk about CRDs. CRDs stand for Custom Resource Declarations. These are definitions that are added to the default Kubernetes to extend use cases and define new types, new objects, new APIs to allow for more use cases. Also, we're going to talk about YAML files. So YAML is a file format, and it's used to define the specifications to define new objects, for example. So when looking at the whole stack, let's take a server that runs in cloud. First layer is the hardware layer, the physical layer. On top of that, there's the operating system with KVM. And actually, this is important for what comes next. The operating system runs. On top of that, there's the Kubernetes stack. with the orchestrator, the container runtime, scheduling, everything Kubernetes related. And that, yet on top of that, there's KubeVirt. And at that level, we can find libvirt, QEMU, and that QEMU is actually using the KVM we were mentioning before.
So how does it work internally? So we have two sets of components. We have one first set that is running on control plane nodes. That's what we call named cluster component in this. So those are special nodes running privileged containers. We have some new set of controllers or pod deployed there by KubeVirt, so Virt controller, Virt API, and we also have worker nodes on a Kubernetes cluster that are running typically the workload that you want to deploy, let's say a web front end or anything else like that. And in the case of KubeVirt, it will be virtual machines. So how does it start? It starts by a YAML file that you will define your virtual machine using a specific type of object, as a new CRD for a virtual machine. You will write this file, use kubectl command line tool to push it. So on Kubernetes side, it will be received by the API server. The API server will analyze this YAML file. And internally, the Virt controller is watching for new event, the creation of a new virtual machine. So it will take this YAML file, analyze it, and then later on, when you will start the virtual machine, through the virtual API that will receive this request, the virtual machine object will get scheduled onto a specific worker node. And on this worker node, we'll have a specific pod named Virt handler that's deployed as a daemon set. So it's running on all the nodes of your cluster. And in that case, then it will analyze the YAML file. It will instantiate a new pod that's named Virt launcher that we see here. And in this new pod, we'll have an instance of libvirt that will be running. And we will also later on have an instance of QEMU. So this file from YAML will be translated to XML. It's the domain XML format from libvirt, received by a pass to Virt launcher through a communication mechanism, pass to libvirt, and then libvirt will use this XML to use vir.sh and then create an instance of QEMU using this file. And if you're using hardware acceleration, it will also use KVM behind. And one important thing to note is that it's not a new CRI like virtual machine and Kubernetes. Sometimes you might have heard of gvisor or kata container, which are CRI. And in this case, you create your pod within a VM. In this case, we have standard pod running Linux processes, so QEMU, that will then create the virtual machines. And if you create multiple virtual machines, you will have multiple instances of the Virt launcher pod, with each time its instance of libvirt and QEMU. So that means that we have new CRD, new types of resources, new backend function to handle those, and new API. So in the sense of your Kubernetes cluster, you're increasing your attack surface.
So let's say you want to start using KubeVirt. Where do you start? It's actually quite easy. So you have your Kubernetes instance. You need to enable first the KubeVirt add-on. Then you will install the virtctl, which is a helper here. You will create a YAML file to describe what VM you want to create. And this is an example of a functional YAML file, like a small one. So, for example, here you will define it as the kind virtual machine, and some fields are mandatory, like, for example, the VM name. And this is the place where you can specify all the specifications for your VM, like, for example, the number of CPUs you may want, the kind of storage you may want, all those details. Or if you want a GPU, I mean, you got it. So you create your YAML file, and then with kubectl, you can apply it. So kubectl apply your specifications. If everything is correct, then it will create the VM. Once it is created, you can start it with virtctl. And then once the VM is started, you can get a shell onto it with console. So we had to think about the threat model. As a cloud provider, we wanted to stay in that scope. And we considered the virt handlers trusted. So the virt handler is kind of the broker for the virtual machine, so dealing with the whole logic, and also the cluster components, like everything related to Kubernetes, because we considered it was a bit out of scope here. And we considered untrusted, everything tied to the user or related to the user, like, for example, the virt launcher, the VMs, and also all the workloads on the other workloads on the Kubernetes cluster. And we had to think about the ways to attack KubeVirt next. And actually, first, as it's a virtualization solution, like all the virtualization typical threats had to be considered, like, for example, devices pass-through, to name one of them, but also threats coming from the combination of containerization and virtualization. Like, for example, guest-to-host bypassing the sandbox, using the file system, the network, reporting, but also other kinds of problems like encryption or race conditions, or actually many other ones. So I'm not going to go over all of them, but just to say, yes, okay, we considered a bunch of threat vectors. So looking at all that, where to start? So the approach was to start gathering some background information, then define the threat model, do some scoping. We got some first bugs at that point, which was very encouraging, but also we scaled it a bit. We defined a security roadmap. At some point, we had 9 security reviews, 10 reviewers on it. We created some ramp-up material to help them. Well, that was kind of big at some point. Some magic happened, and here we are to present the findings, reports, fixes. So yeah, let's get to the findings now. So first thing, something we didn't mention. KubeVirt is written in Go. And Go can be, to some extent, considered as a memory-safe language. Well, to some extent, because there's a garbage collector, but it doesn't give the same assurance as, for example, Rust. Okay, but we looked at some, so we didn't look at those kind of bugs, but we looked at other bugs such as path traversals, which are very common in Go. And actually for that, Oliver Brooks and James Klopschick of NCC Group raised awareness on risky patterns for KubeVirt, so risky functions that may be susceptible to, may be prone to such attacks. And here is the kind of syntax that may be problematic, like file path that join on a root and a child path. So a function that joins root and child path together to form a new path. So why is it a problem? Why may it be a problem, actually? Well, if one of the arguments is derived from user input without sanitization, also if that function is in a piece of code that does sensitive operations, such as, for example, mounting path from the host into the pod, and if there's no security policy that applies, then you may consider that code as a problem. Like if you take a mutable root, but a child path that is, for example, .. text.txt, then the join may not have the expected outcome. So that's what we were looking for. First attempt was to do a grep on such functions, and there were lots of results. So next thing was to trace the arguments up. Then create some tailored VM specifications. So why do that? That's because the user actually can choose what VM they want. So they can manipulate the parameters, and that's how we craft something derived from user input. So creating some VM specifications, which parameters are then used by the potentially vulnerable functions. So this is an example, like with name being .. //test_VM, because one of the functions was consuming that. However, this didn't work, because there are some checks done by something that is called the admitters that checks all the content of the VM specifications. So, okay, how to work around that? Looking closer at those VM admitters, there are a list of functions that handle specific arguments, which means that by default, everything is allowed, but the admitters check for some values or check for some parameters in particular. So, for example, here it checks some behaviors on devices' inputs. The question is, how can we find the hole in that? Like, how can we find a parameter that is not filtered or not enough? And one of the cases was super interesting. It was in containerdisc.go. there was a join function, and that function was mounting path, so from the host into the pod. And this parameter, like image path, the second one was derived from 3 different sources, and one of them actually was not checked by the admitters. So the next attempt was to create specifications, create a container disk. I'm not sure you can see it, but in the specification, there's volumes. Under that, there's container disk, a legitimate image, but the path is crafted, test 3, then lots of /... and etc password, because that's what we want to read to check that it works. And from within the VM, it worked. So crafting the VM specifications, we start the VM, and then from the VM, we can read etc password from the host. So from the VM, from the container. So thank you. And that was CV 2022-1798. And there are more details in the security advisory.
Then something else that we looked at is KubeVirt design that's well made. They split the virtual machine handling on a node in 2 pods, Virt Handler and Virt Launcher. And QEMU is running in the Virt Launcher instance, but this is an unprivileged pod, so no privilege on the system. But QEMU, if you use hardware acceleration, it requires access to Dave KVM. So how can you be unprivileged and still get access to something that interacts with the kernel? So that's how it's using actually the device plugging framework. This is a component of Kubernetes that allows you to develop specific pod that allows to expose a device that's local to a node onto other pods on the node. So you need a privileged pod. That would be the device plugging. That would be privileged. That's using its privilege to expose something onto the cluster, local to a node. So when you want to develop one, you specify the device you want to expose, and then you register some callbacks that will be called when a device will get a pod will be scheduled requesting this device. And when you want to request access to this device in a pod, you specify the spec containers resources request information, and you say, I want to access this device. And then if you have privilege to deploy a pod, you will get scheduled onto a node providing this type of device plugin and get access to this device. In the case of KubeVirt, they use this method to expose multiple devices, Dave KVM, Dev 10, and Dev SCV. If you have a device plugin that's deployed on a node, if you look into the specification of a node using kubectl and display the information like as a YAML file, if you look under the capacity section, you will see in this case that you have devices.kubevirt.io, KVM, SEV, and 10. And in this case, we have 1,000 device of type KVM. And if you want to use it, then in this case, you have your YAML file, and you just specify that it's a pod. You choose your image, what you want to execute as a command. And then in the resource section, you say that you want at least maximum 1 and at least 1 quantity of a device. The quantity is useful when you have really like physical devices, like let's say a GPU or network card, because you have a maximum number of client or VM that can connect to it. In the case of KVM, it's almost limitless. And then you use kubectl to deploy your pod. And inside your pod, if you execute code in it, you just look at Dave KVM, it's existing. And if you use a tool such as KVM OK, it will just tell you that KVM acceleration can be used. The catch is that there is no authorization mechanism in place on this framework. So even if you use, for example, the handlers that you register when you create a device plugin, you don't receive enough information to do any authorization at that level. So you have to rely on something else, like an admission controller, to do some authorization. So if you're like me and you knew little on Dave KVM, I didn't look into the internal of Dave KVM, you would think, OK, cool. Now I have that, I can deploy a pod, and I can access all the VMs that are deployed there and mess with the VM. Except it doesn't work like that. Dave KVM, and then little did I knew is that Dave KVM has KVM has a pair process isolation. So when you open Dave KVM, you receive a file descriptor. And then in any IOCTLs that you perform, you have to pass this file descriptor. And in the module implementation, it will isolate every client that connects to it. So you have a pair process isolation. So if you have process B creating a VM, and process A creating a VM, process B creating a VM, process B cannot mess with the VM from process A, unless process B has some kind of, you can inject memory in process A, like a shellcode, and then make the shellcode access it. But that's something else. But by default, you don't have that. And looking at the IOCTLs that we have, OK, you can create a VM. That's fine, but to elevate your privilege, you might want to expose or exploit some vulnerability. And we can say that the IOCTLs that you have in this case, they could be considered as pretty safe because they have been audited quite a bunch and also fuzzed and everything. So no such luck in this case. Then for DevTon, you need to have capped netadmin privileges. And then you can do some things on the network level, but still it requires some privileges. And what we wanted to see was if you have no privilege other than deploy a pod on a cluster. Yet for Dev SEV, that's something else. Dev SEV is related to AMD SEV, which is a technology that allows on the processor level to encrypt the memory pages of a virtual machine and prevents the hypervisor from accessing the virtual memory of a guest. That's used in confidential computing. In each case, Dave KVM, Tune, and SEV that allows you to interact with the kernel. And as such, you have an increased attack surface. And here, it didn't show during our research because the developer of KubeVirt directly removed access to Dev SEV and put it behind a feature flag that's not enabled by default. So it was actually there's no safe. But a few months later, our colleague Andy, known as DeFlow, did a research on the SEV kernel module and discovered multiple memory leak vulnerability that allows to retrieve information, memory from the kernel from userland. So that's a clear example that by exposing more devices, you increase the attack surface. So in our case, Dev SEV was removed. Then we looked at something else. In this case, we have no findings, but we still put it because it's interesting considering the attack surface and what we have with KubeVirt. So we ask ourselves, OK, if I can create a VM, can I request any device on the host? Let's say the host has a GPU. Can I just request access to the GPU? Or any other type of device? We can think about other type of deployment where you can have a specific device deployed on the node. But what we found is that all type of devices that we can say as pass-through devices, mediated devices, and SRIOV are requiring a configuration at the host level. So unless an administrator on the node could be done by Ansible or through script, but you need administrative access to the host and do some setup before you can assign it to a VM. In the case of pass-through devices, if you want to share your GPU with a VM, you have to unbound it from the host to allow it to be bound to a VM, because there is a 1-1 mapping between those devices, like standard GPU card, and a user or client of this device. And on top of that, there is a field in KubeVirt that's called permitted host devices, where you have to list the allowed devices that VMs are allowed to use. And just a related case is SRIOV that falls back to those permitted host devices. SRIOV, if you're not familiar with it, it allows a graphic card to kind of duplicate itself. But the duplication is kind of made on the device level. So that allows, for example, if you want to play Windows game on Linux, so you have a Windows virtual machine and you have your Linux host, you can have both the Linux host and the Windows guest sharing the same graphic card, but there are some code in the graphic card that handle that creates a kind of virtual clone. But when you do enable or create a virtual clone, then it appears in the PCI device tree on the host as a device, and then you have to list it in the permitted host device as well. So in this case, same, you have to do some configuration there. And the case for mediated device is another type of device, and you need also configuration at the host level. Then we look at something else related to Kubernetes, which are privileged service accounts. That's something that was highlighted during KubeCon EU 2022, so last year. And in short, this is something that is related to overprivileged service account. So let's say you have a pod running on the cluster, and this pod needs to do some specific action on the cluster. Maybe list the other pod on the cluster. Maybe do some management of the node. To do that, you need some privilege on the Kubernetes cluster itself. And what you can do is create a service account on Kubernetes, give it some privileges, like modify nodes, modify pods, or list data, and then bound this to a pod. The issue is that then the KSA, so Kubernetes Service Account, the token is available on the pod's file system. And this means that if you have root privilege on the host, then you can just go to the pod file system and access the file, if you have those root privilege. And the thing is that we don't consider Linux namespaces as a security boundary, because there are currently a lot of kernel vulnerabilities. You can also have misconfigured pod that allows like host path that allows directly to mount a pod. So it's difficult to consider that as a security boundary. So we say that anytime you have a pod that's either malicious by default or that gets compromised, then we can get access to the KSA token of any pod that deployed on this pod as well. And then if you get access to a KSA token, you can do probably lateral movement or privilege escalation depending on the privilege of this service account. In KubeVirt, we didn't find any KSA. And there is also a proper node isolation, meaning that everything that's privileged, like the Virt controller and Virt API, they do have service account with high privilege, but they are running on control plane node. So anything you will deploy on the cluster will not get on the same node by default, due to a tainting mechanism in Kubernetes. But in the solution that we audited, we found that we deploy additional components. And one of those is deployed as a daemon set, meaning that it's deployed on all the pods of all the nodes of the cluster. So that's a win, because if you compromise one pod on the cluster, you're assured that you will get this privileged node, a pod running on the same node. And this service account had the get, watch, list, update, and patch privilege on nodes and pods object. So if you have get and list on pods, for example, you can list the YAML or the definition of a pod. And if, for example, you do something that is not a good practice, but passing secrets through environment variable, you can just access the environment variable and get access to those secrets. And if you have access to the nodes, you can probably steer away a pod onto a node and then try some other types of attack. Then we also look at third-party attack surface, because you might want to add additional components. For example, if you use a graphic card for ML workloads or things like that. In this case, we did some checks, and so check for something like curl pipe SH, which doesn't give you provenance validation on the things that you install. Also check the version of the driver, so you get an alert when there is a new CVE, or some things that could be specific to your threat model. But if you have a VM using a GPU, and the VM is deallocated, the GPU is then used by another VM. If you get a compromise of the GPU in between, an attacker with specific privilege might be able to bounce between the VMs. So you might want to also reset the GPU when the VM is deallocated. Then we also look at other areas like cryptography, networking, internals API. And we found other findings, like for example, KubeVirt didn't have any fuzzing harnesses, so that's now something that's work in progress. Even if Go is memory safe in a way, then you also have other types of vulnerability, and their fuzzing harnesses can help you find those and also like help the stability of the project. We also did found some concurrency issues that didn't lead to security issue, but that's still good. That allows to override some information. And we would like to thank our colleague in security who also worked on the review with us, and especially Roman Moore, who is our point of contact for KubeVirt and is doing a great, amazing job there. Then, speaking on remediation and hardening, some common Kubernetes recommendation that we want to give. Those are not exhaustive, but those are ground rules. Like the first rule of the Kubernetes Security Club is that you don't mix worker and control plane node. Control plane node are running high privilege pod that have privilege over the cluster. And if you have worker node that are supposed to run your end user workload, you don't want those end user workload scheduled on the control plane node as they have access to the KSA of the control plane pods. You also want to review the airbag manifest when you create those overly privileged service accounts. And you want to do this using either you can do your own tooling or use commercial solution that will integrate in your CI/CD pipeline. If this is not enough and you want to have more fine-grained validation, you can use admission controller to fix those airbag gaps. And you also want to implement further, as said before. Then, regarding the admission controller, before you had pod security policy that has been deprecated, and now you have pod security standards and admission. So that allows you to have 3 big classes of policy that you can deploy, and then assign a pod to a specific group of policy. And you can say, for example, I don't want to have privileged pod start by anyone on the cluster or in a specific namespace. And then if you need more fine-grained outside of those 3 big classes that they have, you can use a custom admission controller or existing one, like OPA Gatekeeper or other like KubeVirt, those kind of solutions. So those are also recommendations that you want to have, like privileged pod, no access to host path, network access also to be limited, and access to devices. Then regarding KubeVirt, you might want to disable some features. So features are behind something named feature gate in KubeVirt. And for example, here you might want to disable host disk and experimental Virt IOFS support because those by default allows you to get access to host file system. At the virtual hardware level, anytime you have a virtual device that you add or is accessible from a VM, you have an increased attack surface as well. Those devices are implemented in the VMM, so QEMU. And the more you have, the more attack surface you have. So here you want to keep things in check and have a limited number of virtual devices. The thing is that KubeVirt for now is not exposing all the QEMU devices that you might have if you run just QEMU and list devices. KubeVirt is limiting that, so that's a good thing. But still, something you might want to do, for example, if you want to enable Spectre v2 mitigation, using your admission controller, you want to limit that the CPU type, for example, is ending with IBRS, so you have only VMs with Spectre v2 mitigations. Then also, on the virtualization side, you might want to take a look at nested virtualization. That's a part of KVM that's complex enough to probably still have some bugs lying around because it's a complex topic. There is a blog post from Project Zero on that. Should you be using it, you can use, for example, seccomp rules on the pod level to limit the IOCTLs that it can use. If you want to have a look, gvisor provide some filters like that in the source code of gvisor, should you need nested virtualization.
Regarding the CV we mentioned earlier, first, the developers need some time to fix it, so we use some workarounds. So as Julien said, it's better to disable features that are not used, so the hot plug volumes were disabled. Also, it's possible to set admission controller policies to tighten it. And if SLInux was enabled, it was not possible to exploit the vulnerability. And then a proper fix was issued. A package was added to the KubeVirt code that is called SafePath, and that handles all the problems related with the path. And it was patched in version 0.55.1. And an example of that is the function join nofollow that replaces that replaces some join cases. This is not something standard to the Go library, by the way. So this is a problem for many Go code, many projects using Go code. So as a conclusion, even if we presented some findings, we can start by saying that overall we witnessed a good architecture and code quality. Also, it's always an interesting topic because it's a virtualization solution, and yet the threat model and attack vectors were different from a traditional virtualization solution. Lots of problems were on the integration layer, not on the product itself. Multi-tenancy is also a risk factor that you want to minimize as much as possible for such problems. And some healthy guidelines can be followed, as we explained earlier. Thank you for your attention.